Hello friend, we've been renovating an old Welsh cottage. As part of that we installed our own underfloor heating system, along with an air source heat pump. This video is going to be about how and why we went to the ridiculous lengths we did to construct the central heating system we've now got. We're going to add underfloor heating to two different kinds of floor. A floating floor with wooden joists like this, and on the ground floor it's a solid concrete floor with insulation and then rotten chipboard above that. Both of them will be wet underfloor heating going to a heat pump and the same manifold, but the details are going to be quite different. Let's start with the wooden floor. The chipboard has arrived, complete with one or two broken tongues. You know what they say about when the only tool you have is a hammer, all you see is nails. I think the same is kind of true if you make your own CNC machine. Every project looks like an opportunity to learn it a bit better and to push it a bit harder. Now we have that fence, we can get each board into the same place easily.
Right, here we go. I think we're okay and aren't going to crash. We'll see. 12mm round over bit.
It's a little bit of a scrap one, that edge. It's going to come off anyway.
Not only did it plunge the whole way into this 22mm chipboard, it also did some routing across, which is quite impressive in its own right, but not what we wanted.
I'm slowly learning the lesson that if you're doing a whole new project with a tool that you haven't used before, even though you've just zeroed it, it's worth doing an air cut just to see what's going on before you do any kind of scoring pass like this. Anyway, that was more of the depth we had in mind. And you can see there the dust extraction is very poor. More on that later. I suspect you're wondering why on earth would anyone want to route their own chipboard for underfloor heating anyway? You can just buy them pre-made. The trouble is, everything off the shelf looked to me to be quite suboptimal in terms of efficiency. At least that's the story I've been telling myself, not that I just fancied the project. Here we go, look, and we might have wanted a bit more space. It's quite a tight fit. Seems just about flush though. So I guess the depth is about right, as we want the pipes pushed right up against the floorboards above, so the heat transfers well.
Okay, so looking at it, it all worked quite well. A few tweaks needed. Where the tongue is, it didn't quite get through there.
I knew I'd want to put 8x4 sheets on this machine occasionally, I just didn't think I'd be doing it very often. So I made it so it would fit a full sheet, but it can't actually machine to all the edges of it. Making it that big would have taken up too much workshop space and compromised further on other nice traits like ability to machine metals. These floorboards are 8 foot or 2.4 meters, so I know I'm going to have to flip all of them. With the fence to push them back against, I figured that wouldn't be too difficult. The only tricky element to this is one side's got a tongue on, the other has a groove, so they're not exactly symmetrical. But after some head scratching and learning about work offsets a bit more, we could offset the X and Y by the distance of the tongues and essentially get a nice reliable flip. In fact, I'm semi-amazed that we didn't have to scrap a single board in this whole CNCing adventure. But don't worry, I did make up for it by underestimating the number of total boards we would need by one. Got that done, minus the bit where we've run out. Let's put some floorboards down. Great, first one down. Yes, it feels quite solid. I feel almost that we could have got away with a 16mm channel in that. A 16mm or bigger pipe would have been better because it resists the flow of water less. Oh yeah! Yeah, pretty good. Okay, let's rewind. Before any of this, we need to do a heat loss calculation. We're using the MCS one. It's free and I'll leave a link in the description. To make such a calculation is easy but time consuming. You go around measuring all the walls, floors and ceilings, the windows and all the build materials and their U values, etc, etc. You plug them all into a spreadsheet like this. That way you can calculate, or rather the spreadsheet can calculate, and you can design the system that's perfectly sized for the amount of heat that gets lost from your property from all different surfaces. So it's not too big or not too small, which seems to be a common problem with heat pumps, or heat pump installations at least. Now, professionals doing this have to make a bit of an educated guess about most of the insulation and materials used. We've been in and around most of the surfaces in this cottage, so we've got a bit of an advantage on that front. If you know the thickness and the U value of the materials you're using, like this aerogel insulation we're putting around the window reveals, then you can really accurately calculate the heat loss. The bottom vapor membrane thingy is down. Words of insulation. Toasty. It's especially nice to have the floor well insulated if you're doing underfloor heating. In our case, it involved tearing up the old chipboard, which was trash anyway, and saving the joists, which were perfectly fine. But that did mean a lot of denailing, so much so I bet most people would have just ditched the timbers. That would have been a shame though, because they'd already survived quite an epic damp problem, so they deserve to carry on. Time will tell, but hopefully the weeks me, Sam and our friend Hal spent developing hand calluses will solve that damp problem by diverting this mini stream round the back, down the side and away from the cottage. There's something about clamping a workpiece down with big firm steel clamps right in the path of the spindle that definitely makes the heart speed up a bit. At this point, I wasn't even using a very significant feed speed. It's something like 8,000 millimeters a minute. But having struggled to lift that gantry with Sam helping me into position, it sure seems like a lot of weight to be flying towards another solid object. I went up to a feed rate of 15,000 millimeters a minute. Out of the 25 or so boards I machined, I'm not sure if any of them were exactly the same. I was tweaking the settings each time. I did settle in on a feed speed of about 10,000 millimeters a minute though. It sure could have been quicker, but I wasn't in any great rush, and after you've spent a very long time making a precise machine like this, you do tend to coddle it a bit. Well, that and push it to crazy extremes, I suppose. The limiting factor in the end seemed to be the dust extraction, which just couldn't keep up with the higher speeds. We're using a shop vac hooked up to one of those fairly cheap cyclones. The dust shoe, as you see it here, is one of the first things we made on the CNC machine. It's a bunch of cut-up paintbrushes with a completely classic design just out of plywood, uses magnets to hold two halves together. It's way better than nothing, but the reason it doesn't work fantastically well is because it's designed for a high-volume, low-pressure extractor. That is to say, something with ducts and a large hose diameter. Not a shop vacuum anyway, which is more of a high-pressure, low-volume kind of animal. When you've got high velocity air but not much of it, you really need it right at the source of the dust before it gets a chance to spread out. And that's what that bizarre dust shoe inside the dust shoe type thingy was. And believe it or not, that was actually a really big improvement. The flow resistance of 12mm underfloor heating pipe is quite a lot larger than 16mm, and this leads to one of the big problems with using it. That is, the total length of each pipe run is limited. Go above, say, 70 meters and the circulating pump in the heat pump is going to struggle to push the fluid round the system. One solution, which seems common, is to increase the pipe spacing so that you essentially have less pipe in the floor. Commercially, this is what you see in that it's really hard to buy boards that have spacing of less than 150 millimeters. Ultimately, what this means is you have less emitter sending out the heat. You have to run it at a higher temperature and the heat pump will be less efficient. The whole reason heat pumps work so great with underfloor heating is that compared to radiators on the wall, the floor is a really large surface area. We don't want to lose this great advantage just because it's a bit tricky to fit the pipes in there. So hopefully with our tighter pipe spacings, we can have the flow temperature lower and the heat pump will run more efficiently. Here you can see ours, for example, at 35 degrees C flow has a SCOP of 4.41 versus, say, a flow of 50 degrees, it's only 3.37. We could go into what SCOP means, but essentially the higher the number, the more efficient it's running. Of course, tighter pipe spacings means more pipe in a given area, leading us back to the initial problem of the pipes being too long. The way around this is to split each room into multiple loops. Typically, this would make designing, installing, routing, the pipe work, and all the rest of it much more difficult, which is a big problem unless you kind of fancy the challenge and you want to make custom boards. Okay, here's how we're doing. We've got that mounted, going all kinds of routing. Over here, we've just been drilling holes. And this is where the pipe is gonna go through the wall. We're just using some old hula hoop as sleeving. The cottage itself is really quite small, but it is on 3 different levels on the slope, as it were. So the final design of the pipe layout was based on a few things. The tightest bend radius of the pipe, where we could squeeze the manifold in, ideally towards the middle, and how long each loop could be before the circulating pump and the heat pump would struggle and would need help from an external pump, which we didn't want. I'll leave a link to a great video by Urban Plumbers who shows how to calculate things like the flow rate for a given length of pipe to give you a certain temperature drop between the flow and return on the pipe, or the delta T as people like to call it. In terms of fitting the pipe, let's just say when I made the living room boards, which are the last ones I routed, I made the grooves slightly bigger so that they went in a little easier. It all worked out nicely in the end and I didn't have any problem with them popping out, but they did require some mild persuasion. The pipes are very hardy really, but you know, a flooded chipboard floor is still a flooded chipboard floor, so yeah, lots of vacuuming out of the grooves before installing. Quite useful to have these open-mouthed chamfer jointy things, so the very slight mismatch of the boards can be easily accommodated. And then any movement in the future, which there shouldn't really be differential movement between the boards because they're both screwed and glued. To route all the grooves in all the chipboard panels, we used 3 carbide end mills, 12mm ball nose ones. Between them they had about 1,000 linear meters to machine out. It's quite abrasive stuff, you can see all kinds of particles in there, but of course it's not the only way the router bits ended up getting blunted. Mishaps aside, we might have improved the longevity of the cutting bits by improving the dust extraction a bit more. We made this polycarbonate dust shoe that picks up the dust much closer to source. It moves independently of the Z-axis. On flat boards like this, it works better than expected and let me up the feed rate so the chips being removed were slightly larger. It means that almost nothing is left behind to be recut, which also contributes to dulling. You can see on my prototype how the airflow inside could be a little smoother and it could be fabricated a bit better, but the principle is great. I will have to iterate on it and somehow modify it for the end game of auto tool changing, but for now it's good. Just to be clear though, I can overload the system when I really push the machine. At reasonable feed and speed, dust collection is almost total, but it's still the limiting factor when I go fast. After cutting, you need to use this re-rounding tool, which also puts a chamfer on both sides of the pipe. I haven't seen anyone else doing it, but it seems a good idea to give it a good vacuum out before the Euro connectors go on like this. There's a rubber seal on the inside of the pipe and to the manifold. These connectors don't need to be super tight, and out of all of them there was only one that was a little bit fussy when I came to pressure testing. Okay, that's that. Which makes this room done. Pleased. It's going to be the sharpest turn so far, so slightly nervous. This was still well within the specified bending radius of the pipe, but I wasn't too happy about the misalignment between the rooms. So, it'll do. Only back down the stairs to go. Another loop done. So now we've done 2 up in the bedroom here. So the bedroom back there is done. We've got the living room to do, and that's all the ones that are routed out chipboard. Wow, that was truly an abomination. I don't think anyone could live with how horrible that was, so I've cleaned it up a little bit. Wire brush and like point blue pour torching to flick off the droplet, and then a bit sanding. Every sealed central heating system like this requires some kind of expansion vessel. Pressure rises when the temperature goes up. Without something like this to take up the slack, things go pop. Right, abide by the arrow. Air vent goes at the top. Some kind of centrifugal separator stroke magnetic particle separator down there. I can't honestly see there's going to be much for this to do, considering there's no radiator, there's no steel radiators anyway on this whole thing. Oh, that worked better than I thought it would. Great, okay. So you see it's basically quite a simple system. It's quite crammed into the side and corner there. There's such little room in this cottage that every bit is quite valuable, so it's quite cool that we could do this ourselves. Last thing to go in will be data, like the data unit or whatever you call it up there. Got a cable down there ready for that goes through the stone wall with those pipes. Getting through there was interesting, I can tell you. It's my birthday and Sam obviously thinks I'm mad spending the morning doing the last loop, but it's quite exciting to get it done. Here she comes. It becomes awkward when you're uncoiling in opposite directions to the way the curve goes. There's a definite knack to unwinding and laying out the pipe without having it twisting, which could potentially lead to kinking and is generally undesirable. Well, it's arrived while we weren't here unexpectedly. Let's make a space for it. Luckily, we don't have to dig too deep as it's very hard shale anyway, but I'm sure we overkilled it. We're making 2 little silly stone walls just to contain the concrete for the strip foundations. Okay, here we go. Doing a bit of ramming. Here we are, 2 nice odd shaped blobs, roughly level, roughly smooth, quite deep. Concrete's got to be really quite stiff to be able to do it above formwork like that. Okay, that's the data cable coming out of the wall, and the pipes there come down, they're all ready at the foot. The stainless steel pipe clips here go round the insulation so they're not a thermal bridge. Moving the heat pump into position was interesting. It's kind of heavy, but more a little bit awkward. One end's a lot heavier than the other, and we had some interesting terrain to navigate. We had 2 pre-arranged stops where we'd put buttons down where we could put it down, and only one little sit down on the job. It's a Valiant Aerotherm Plus, 3.5 kilowatt. We got the extra damping mounts, but after feeling and sort of seeing how they work, I think I'd rather have saved the money and made some from some old tyres. I doubt if it really needs to be precisely level, but before we bolted it down to the concrete, we went ahead and shimmed it that way anyway. Of course, we've given in to curiosity and opened this up. It's very simple to take the case off. Sound insulation on most of the panels. It all looks quite decent and robust. Let's have a look at some of the main bits. Here we've got the main heat exchanger, the circulating pump here. This is where the tails come out. Got a flow meter on the return there, I guess that is. Flexible rubber hoses, temperature sensor. I think this back here is probably the compressor. Electronics box in here. There's the compressor inverter electronics in there with its little heat sink. I guess that gets a lot of oomph from the fan going. There's little clips on that would be for balancing. Looks fairly basic. And then of course the big radiator back there. I mean, it's big, but it's not ridiculous. Temperature sensor coming over here. It's not the most fantastical quality detailing there. And that just goes to a temperature sensor outside there. This whole housing here is kind of surprisingly just a dense polystyrene, almost like a packing crate. But I guess it makes sense and does the job. This here looks a bit shambolic. Yeah, there's double-sided tape on that, so clearly that should be stuck to there. But looks like there's probably not enough room for it. This heat pump uses R290 or propane as the refrigerant. Compared to some others, this limits where you can position the unit. It can't be, for example, alongside a window, or you may, if there was a leak, end up having propane leaking into the house. For the same reason, when it's serviced, the service engineer should really have a gas sniffer to make sure there's no gas leaks before even taking the cover off. A gas sniffer's not a hugely expensive piece of kit. I didn't really realise I'd need it for any kind of maintenance before selecting this unit, so there's that. About to turn that. Once I do, I'm going to have to sprint it next door to see whether it's leaking or I can hear any air hissing, and then sprint it back if there is any, because I don't want the chipboard getting soaked. Here goes. It's quite stiff. Stroke stuck. Let's go, go, go. Looks alright down there. About to connect the flow main pipe work up, but just before I do, I'm giving the system a good flush through. This is an inter ball valve that reduces from 1.25 inches down to a male inch, and then we've just got this inch straight socket, goes to the inch anti-drain down valve, and that's got a little bushing on taking it back to 1¼ inch, which the Valent flexi hose attaches to, and that goes off and onto our 28mm pipework. Amazing how much debate can be sparked just by the use of these anti-freeze valves. There's 3 options. You can put glycol in, you can use one of these, or you can use 2 of these on the flow and return. Well, I suppose there's 4 options. The other one is just to not do any of that. As long as it doesn't freeze up when there's a power cut, that's the only thing. So this seems to be the manufactured recommended way of insulating the drain down valve. Use a hole saw, cut a hole in the bottom and top. There's a little hole there in the top. That just breaks the vacuum and allows it to drain. It seems surprising that this is the best they recommend for insulation, considering you'd want one of these valves as an alternative to glycol to make the system more efficient. But you're leaving like a terrible cold bridge here and here to the pipe. So we'll see if we can't do a little bit better. A little better, at least it'll be protected from direct wind. Still lots of cold's going to get in there, as well as water. My solution to that is a little cut off of a bore plug type thing, and then I'll just patch over the top. We're going to try filling some loops and pressure testing. We've got a towel down the hose that's just going outside. It's just a garden hose. That's going to take the return, and we're connecting this here up to our mains feed. This is just a tap connector. To fill and purge all the underfloor heating loops, we isolate from the heat pump and then just isolate each loop in turn. I set the hose up so it was quite uphill of the manifold, in the idea no air would come back into the system. Then we're just running through until it's a nice clean stream and no air is coming out. Now to get ready for the pressure test, I'm going to open them all back up. They're all quite evenly flowing, which is definitely a good sign. Now we're just going to slowly turn this off. There we are. So they've stopped flowing. We're at mains pressure. Shut that off. Turn that off. And this is our pressure. Now we'll recheck it. Okay, this is literally just moments later or minutes later. It's gone up to almost 5 bar. Presumably this is because the cold water from the tap is getting to room temperature in all these pipes. That continued over the following few hours. We let some pressure out. This test is much higher than the normal operating pressure, and you do have to be careful if the sun comes out and shines on the floor. Yep, the bedroom is almost getting there. We've got this engineered pine with an oak veneer, which of course is branded as engineered oak. You can see it there. And it's pretty nice, I think. It's pretty nice. They go together all right, these click fit things. A little bit infuriating if you're in a rush. Here we are, all ready to lay down the finished floor. Sam's done some painting, and we've got a bit of a problem in that this board here by the door both moves and creaks. Let's see if you can see that close up. It's not adequately supported down on that edge, despite me trying my best to get this just level. I obviously mucked up that bit. What can I say? It's very frustrating, but no shortcuts here, I don't think. We're going to have to take up the pipes so we can get this particular board out. It's a 2 steps backwards thing, but yeah, can't skimp on it, I don't think. It's the kind of thing that'll only get worse with time as well. To that end, I've already taken the sliding door bit out, which was difficult in itself because it involved me having to cut away some of the plaster so I could lift it up enough to get it off its tracks. So we've done all that fun. Now it's getting the pipes out, which my very quick try suggests it's not going to be easier to. In fact, without using a sharp tool, which would risk damaging the pipe, I found no way of doing it other than to sort of take all the pipe up from the end. Once that was done, though, it wasn't too difficult to semi-smash the floorboard up. After some umming and ahhing, shimmy and anchoring, we were back in business. Doors back, pipes back, flooring has begun. This combi saw is super useful and does do great quality cuts. Maybe that's because it has a blade that's pretty big for a miter saw, or maybe it's because it's got no sliding mechanism to cause slop. But it's a bit more time consuming to have to flip each board over because it doesn't quite have the capacity. I do basically never use the table saw element of it though, so I might look at changing it at some point. I do sometimes wonder what a person of 100 years ago would make of these machined click together edges on these wooden boards. They make it really quite easy to fit, and none of this top layer of floorboards is fixed down. It just becomes one big sheet that floats on top of the special underfloor heating underlay, which as far as I can tell is just regular floating floor underlay that's thin and has holes punched in it. The more experience I get of woodworking of all kinds really, the more convinced I am that the only true skill is patience and being able to enjoy the inevitable back and forthery as you sneak up on just that perfect fit. We're on to the office down here. Room's changed colour. One problem area can be these bits here. I'm in trouble getting that to lock down. I think maybe the tooling they were using was getting blunt and just wasn't cutting that edge quite deep enough. I'll try and see if we can bang it in. That'll do it. After saying how easily they go together, this happened a few more times. The better way of doing it to get them fitting nicely is to just trim a little bit off the end. And there we go, that's it. The office mostly done. I need to leave the boards on the left unfixed for the pipes that go down to the kitchen and the bathroom are going to run under there. You might be wondering where the hot water tank is, the big thing that would supply hot water to the taps and get heated by the heat pump via a diverter valve. We don't have one of those in this simple system, but why? First reason is space. We just don't have room for a big tank. Second is that anytime you're holding hot water or anything else really at a hot temperature, you're using energy. Third is complexity. There's just much less to go wrong in a super simple system like this. This is the entirety of the plant room, as they call it. Fourth, there was already an electric shower in this place. We don't have a bath. We have a dishwasher. So typically our use of hot water looks like this. Wash the hands. That's it, done. Or wash the cloth. Here's our hot water supply at the moment. It's an under sink unit. Beauty of this is that it's basically instant hot water. There's no big pipe run between a big tank and the tap. So yeah, we miss out on the efficiency gains of the heat pump heating the hot water, but we also don't have a giant tank of hot water that we wouldn't use. Before we start the downstairs, we need a 10-second interlude to make this window a little bit bigger. Doing this first and not dropping any big rocks on the new floor we're putting in seemed like a good idea. We made it so the bottom of the window is going to be kind of level with the worktop height, so that in the summer it'll have a slightly outdoor kitchen feel. The other thing we missed out on doing it ourselves is a £5,000 government grant that you can get if it supplies central heating and domestic hot water, which we didn't want, and you get a certified professional to do the installation. Funnily enough, when we were looking at it, the costings at the beginning, it seemed like we wouldn't actually save that much doing it that way. It probably would have been done quicker, but then we would have missed out on the juicy learning about how all the system works. The decider might have been ChatGTP. I was questioning it about the possibilities of DIY install and heat pumps and things, and essentially it gave me a moralistic scolding for even thinking about doing it myself. I guess the leave it to the professionals trope must be pretty prevalent in its training data. Either way, it spurred me on to have a go. We're downstairs and we've begun. The underfloor heating pipes come out down there. They go round the wall like so. I know that's a little bit controversial. And then wiggle waggle, changing the board direction halfway through the room because it seemed to be the only way it would work. We've got this little nook to do. These overlay boards are 120mm spacing, and they're simply polyurethane glued down to the layer here underneath, which is 50mm of Celotex type stuff. So far it's all worked quite well. The only tricky bits are where you've got to cut out a bit of the aluminium and styrofoam. Aluminium's quite thick, should do a good job of spreading the heat, I think. Just been using the bags there to weigh down while the gluing occurs. So that's the bathroom and hallway. We've got the kitchen to do. It's all going well. There's one of the boards before any modification. Sure, there's a more elegant way of doing this. Towels down. I'll be curious to see whether we get loads of water leaking out of this. Now I've shut everything down. It's been full and running a little bit, testing the upper levels. Now let's get this bathroom one in. It's going to leak anywhere. I think it's going to be these bits where it's going to join to the towel rail. At the moment, this little loop represents the towel rail. The towel rail is doing double duty in this system. Without it, we would have to add a separate volumizer, which we didn't want. Anyway, let's get back to the underfloor. Here we are with the dramatic noise of the pressure test on the system, which didn't leak. The procedure with the polyurethane adhesive is to spray it on, leave it for a bit, and then stick the boards down. Probably we didn't need to add weight to the top of them after walking over them, but we did. We didn't want any voids down there that might weaken the floor. The overlay boards themselves are supposed to be very high density and resistant to crushing. In fact, you're supposed to be able to tile straight onto them. But without treading softly and with my softest trainers on, I found that I could easily make indents in it, so we're not going to be doing that. Luckily, that was part of the plan, or we'd be needing to raise the level of all the doors, and this is still going to be a very low level build height. Quite a big moment. The heating is on, the manifold's complete. Been flushing out the system. You can see we've got flow on all the loops except this one, which is just blanked off. That's going to be a spare. Before sticking anything to the overlay boards, a good degreasing with soapy water is called for. And then we're priming it with a primer with kind of grits in it to add key. While that all dries up, it gives us a chance to prep these hardy backer boards. They're very thin and you can just score them, and then with a bit of persuasion they snap. It's harder when you're sort of at the edge of a board like this, and much easier when you're cutting through the middle of a board. Now as I'm laying these out, I want to stagger all the joints so there's no big long running seams, and nor do they line up with the seams of the overlay boards underneath.
Plop.
To bond on the thin cement boards, we're using a flexible tile adhesive for underfloor heating. This should fill all the voids between the pipe and the cement boards, which, as well as being really strong, are great conductors of heat. After plenty of wiggle jiggling and getting this board perfectly lined up, being the first one or the others are going to follow, we need to then check the contact area of the adhesive to make sure we've got full coverage there, and also the level of it. Of course, it's such a big board, once it's down there, pretty hard to prise up. Okay, look at that, excellent. Just got a little bit of iffiness in that corner, but otherwise just what we want. We'd roughly laid out the plan of the kitchen before laying the underfloor heating pipes, so in the places where cabinets and worktops will be, there's just scrap pipe. We don't really want the cupboards to be heated, and the pipes are just there to fill the voids in the overlay boards. We've set up the laser there. We've done a bit of planning out. We've cut some tiles, let's stick them down. It's the first time I've tiled with something like this. These are relatively large natural Welsh slates with a riven finish. Levelling and aligning them was interesting. It took me some time to get the hang of it, all the time trying to ensure complete coverage with the tile adhesive. To that end, I was spreading adhesive on the backs of the tiles as well as the floor. This isn't just to guarantee the strength of the floor, but also to improve the conductivity of the heat through to the surface. We use these little levelling aid things. They're really useful, but as you saw, not completely foolproof. Indeed, I still think the key is to put the correct amount of tile adhesive down. On a few occasions I had to lift the tile and add more to make them level. Here we are in the bathroom. We are still going with this tiling, which has taken about 500 years so far. The kitchen's done, apart from the grouting. That's fun to do still. So it's that time, we're trying to clean off all manner of footprints and other sloppy tile adhesive. Any bowls of grubby water later. Here we are, first batch of the stone sealants on those few, so I can just, they'll be covered in worktop and I'll be able to tell what the finished product looks like. Same with in the bathroom there, I've just coated those two tiles. Stone sealer stuff. This is the next game. So it's apparently important to do this before the grouting so the grout doesn't stain. I've had this sealant gun with the capacity to be filled with grout and squirt it out in this method. I've not tried it before. It worked perfectly well, but I don't think I'll be doing it again just because of the extra cleaning out of the gun that's required. Now it's really starting to take shape, and just walking on this floor is pretty cool. Oh, it's gotten cold. It's a frosty cold winter's morning. So the cottage is still far from complete, but we have moved in due to circumstances. The floor's basically done, and the underfloor heating worked great the end of this winter. How is it? The flow temperature is set to about 32 degrees, which means the wood never really gets above 22 degrees, so it's just pleasant. The slate floor down below feels a lot warmer to the touch. Warm hands, warm feet.